So before we go any further, I want to take a quick look at the pseudocode for the fixed point iteration that we saw in the last lecture. But remember that the process here is to evaluate the function at an initial value, that's what I'm calling p, then take that result, substitute it back into the function, and do this over and over until you meet your stopping criterion. And in this code, I've got two stopping methods that we've seen before. First, there's a maximum number of iterations. See that being tested here, and a tolerance value. So what happens is in each pass through the loop, we evaluate the function at the current approximation, then check to see if the difference between the new value and the old value is within that tolerance level. If it is, then we output the result. If it isn't, then we replace the current value with the new value, right? The new value becomes the current value, increment our counter, and pass through the loop again. So let's take a look at an example. To solve this equation using our fixed point iteration approach, we need to find another function that has a fixed point at the same value as this equation's solution. Now, it's always going to be possible to do that just by the brute force method of adding x to both sides. Right? This gives us a new function. Let's call it g of x equals x cubed plus 4x plus 3. And that equation, that function, has a fixed point at x. Now, what I want you to see is that the fixed point of that equation is, in fact, a solution to the previous one. Right? And to see that, let p be a fixed point of g of x. Right? So what that means is g of p is equal to p. Right? But g of p is also p cubed plus 4p plus 3. Right? And if we subtract p from both sides of this, we get p cubed plus 3p plus 3 equals 0. And you notice this is this equation up here, this expression up here, evaluated at p. So that value that is a fixed point of g is also going to be a solution to the original equation. Okay, a quick look at the graph of f of x equals x cubed plus 3x plus 3 shows the graph clearly crosses the x-axis between -1 and 0. So intermediate value theorem, there should be a root in there somewhere. So what I'm going to do is I'm going to take my g of x function here, and I'm going to do this fixed point iteration method with it, starting at x equals -0.5, right? Somewhere in that -1 to 0 interval. Now, if we do that, and I've got the results over here, right? Negative point, if this is my g of x, right, this x cubed plus 4x plus 3, this is g of -0.5, this is g of 0.875, and so on. And you can see that this method goes south really, really, really fast. After just five iterations, we're already way out something times 10 to the negative 10 something times 10 to the 23rd power, which is way far away from that interval from 0 and to -1. So not a good result, right? But we do have some other options, right? We do have some other options. For example, I could take this function here, my original expression, and I'm going to solve it for that x there, right? If I do that, this becomes 3x equals -x cubed minus 3, and then I'll divide everything by x, and I get another function, this one, that should also have a fixed point. At that point, the solution to the original equation. Okay, well, so what happens if we do that? Well, then you get these results. And okay, this sequence does appear to be converging to a number between -1 and 0, but it's doing it really, really slowly, right? It took what 1, 2, 3, 4, 5, 6, 7. It took 7 iterations for us to get to 1 decimal place of accuracy. It took 11, 12 iterations to get to 2 decimal places, and 12, 13, 14, 15, 16. 16 iterations to get out to 3. Okay, I mean, that's nice. I mean, it's giving us an answer, which is great. It's just not doing it very effectively. Okay, well let's try a different approach. Right, I'm going to start with this. I'm going to start with this same equation: x cubed plus 3x plus 3 equals 0. And I'm going to just bear with me here. I'm going to move that 3 over. This will be x cubed plus 3x equals negative 3. Now let's factor an x out of here. X times x squared plus 3 equals negative 3. And then we'll divide by that x squared plus 3. And I get another function, negative 3 over x squared plus 3, that again should have a fixed point at the same place as our original equation has a solution. So if we try again, or try a third time, work our iteration approach with this function, right? Here's what happens. We get a much better result this time. You see, we do appear to be converging to the same result, right? The same number we had over here, only now I got to to the first decimal place of accuracy just after 3 iterations. I got to 2 decimal places after 4, 5, 6 iterations got me to 3, 7, 8, 9 iterations got me to 4. Right over here on the other side, it took, what was it, 16 iterations to get to 3? So much better, right? Much better result here. So the takeaway from all of this, and from what we saw in the previous lecture, is that this fixed point iteration method, it works, right? It can work. It can give us the answers that we're looking for, and it can give us the answers pretty efficiently. However, it's also very much possible for it not only to not work, but to not work pretty spectacularly. So, in the next series of lectures, we're going to see if we can dig into these fixed points in a little more technical detail. We're going to answer questions like, when can we expect a fixed point to exist? When can we expect a fixed point to be unique? Under what circumstances can we expect this sequence that we get from this functional iteration method? When can we expect it to converge? And we're also going to get an idea of exactly how fast we can expect it to converge.